Hi! In this short presentation, we'll discuss our paper, Optimal Network Modification for Spectral Radius-Dependent Phase Transitions. We research networks in order to model complex systems. A network is an elegant structure which is composed of two basic elements, vertices and edges. Vertices are connected by edges, and the edges can also have weights, which are represented here by numbers. Networks are used to model various domains. For example, in this aerial transportation network, the vertices are cities, the edges are flight routes, and the weight of the edges represent the frequency of flights. On top of the network structure, we can apply a dynamical model. This enables us to study domains which change over time, such as the spread of epidemics. A classical model for the propagation of epidemics is the susceptible-infected-susceptible model, or in short, SIS. In this model, each vertex has two states, susceptible and infected. At each time point, an infected vertex can infect a susceptible one with probability beta. Infected vertices can recover and become susceptible again with probability gamma. Then this process is repeated on and on to mimic the dynamics of a disease. The dominant eigenvalue of the network's adjacency matrix controls the dynamics of the system. When the dominant eigenvalue is larger than the ratio of the recovery rate and the infection rate, the epidemic spreads and the network is infected. In direct contrast, when the dominant eigenvalue is smaller than this ratio, the epidemic decays until it is eradicated. In this paper, our goal is to find the minimal change to the network structure, which induces a transition from an infected state and into a disease-free state. There are two strategies to stop the infection process. First, one can remove edges from the network until its dominant eigenvalue induce a phase transition. However, edge removal is a drastic action which can completely isolate a node. On the contrast, we present here a novel approach to this problem. We continuously reduce the weights of the edges. This approach causes a phase transition while at the same time avoids closing routes. To find the optimal set of weights, we formulated and solved the following optimization problem. Using the network adjacency matrix A, we seek a new network W, which is as close as possible to the original network, while at the same time, its largest eigenvalue must be lower than the epidemic threshold. This is in order to force a phase transition. And also, the edges of this network should be non-negative. Our method has several advantages. First, the optimization problem is convex and therefore achieves the global optimum. We introduced a novel optimization method for this problem. We also provide an optimal solution with a focus on edges and another with a focus on vertices. We propose an extension to our method which provides an efficient, discrete solution. Finally, our method is highly scalable and can solve the problem for networks with hundreds of millions of edges. That's it. I hope you will enjoy our paper. Thank you.